I'm very glad to present our speaker today, Professor Roy Lacey from Stony Brook University. He has a degree, PhD degree from State University of New York at Stony Brook. That's essentially the same university, but it was renamed recently. He got his PhD in 1987. He had 3 postdoc positions, 2 of them in France from 98 to 1989, 88 to 89 in Saclay, France. He was at CNRS postdoc from 89 to 90 in Caen. From 1990 to 1991, he was a postdoc at Michigan State University. After that, he joined chemistry department at Stony Brook University, and now he's a full professor there. He's doing a lot of service, participating in many collaborations and working on strongly interacting matter, heavy ion collisions, and many other things that he will be discussing today. So with that, I'll give the microphone to Roy.
Okay, so first let me express my appreciation for the invite, and I hope, of course, that I will live up to the excellent list of speakers who have gone before. I have to also say that I've been watching many of these talks, so I have a good sense of what's been going on. So I'm going to try to make the case that one does observe anomalous transport in the quark-gluon plasma. And what I will say here is that this talk will focus more on the experimental measurements of anomalous transport. And I won't try to give a review of all of the different kinds of experimental measurements, but try to focus in on a particular methodology to try to make the case a little bit more coherent. Let me just say that there have been several excellent talks on, issues, the theoretical issues associated with anomalies. For example, I benefited quite significantly from the earlier presentation by Lance Steiner, for example. So I would encourage people to take a look at that. But the main point that I want to convey here is that the intent is to follow here. I'm going to make a small intro on anomalous transport so you get a clear understanding of what it is that's driving the observables which we try to measure. And then I will go into some discussions on the observables themselves. And I won't go over a diverse set of such observables, again, just particularly focusing on 2. And in addition, I will then show you, rather than go through a whole complicated math exercise, I will try to show you how one can use a detailed set of simulations to gain insights on the observables themselves. You can develop good intuition. And in addition, one can also, in my language, use it to calibrate the signal if you think you have one. And so that's sort of how things will flow. Since this is in colloquium style, of course, it means that there may be details which one might not express at the level of which it would be useful. So let me just point out that much of what I'm going to discuss is summarized in a bunch of papers that I've listed here, and the experimental results will largely be summarized in the STAR collaboration preprint. And let me just also say that, there are also some preliminary results which I will try to include to sort of make the case more straightforward. Now, the main takeaway from this presentation, let me say off the bat so that you can spend the efforts making sure that you follow carefully, is that I'm going to try to argue that we think we now have a good correlator. We can make precision measurements. This charge sensitive correlator, and you'll see in a little bit why it is a charge, why one requires that. This, in my view, indicates anomalous transport in the quark-gluon plasma, and more specifically, anomalous transport associated with the chiral magnetic effect. And so I put this out there ahead so that, of course, you will pay close attention and have your questions ready. So let me begin by showing you a typical Avion collision. And the business here is that this is sort of the standard picture that one draws. So if you follow my cursor, here are the Lorentz contracted ions, which are coming in at ultra relativistic speeds. There is presumably some pre-equilibrium phase. And then we think that we make something which is close to an equilibrated magnetized plasma of quarks and gluons. And if we're lucky, of course, you know, that soup would then restore chiral symmetry, and therefore you end up hopefully with chiral fermions given the right kinds of conditions. Of course, this goes through hydrodynamic expansion. And then ultimately, when the density drops sufficiently, one can then hadronize and make particles, which you then measure in your detector. Now, let me just say that this plasma is really strongly magnetized, okay? And this magnetization really is coming from the fact that you are accelerating ions. So imagine you have a non-central collision. And then, of course, you have these ions which are charged, they're moving, which means there's a current. If I have a current, then, of course, I will generate the associated magnetic field. And this is what this picture here tries to depict. Now, let me just point out that if you make some rudimentary estimates of these magnetic field, they're really, really large. It's like about 10 to the 18 Gauss at Rick, and about 10 to 20 Gauss at the LH3. So compared, for example, to magnetars, you see there are several orders of magnitude larger. So this is pretty substantial. Let me just show another little viewpoint. I want you to just pay attention to the top, not so much this part here. And the essential point that I want to point out, of course, is that if you put out the spatial arrangement of this magnetic field, you can clearly see that it's largely pointing perpendicular to the reaction plane. You know, that's the plane, of course, that would be defined by the beam direction and the impact vector, which separates the distance, or let's say the vector separating the distance between the centers of the two nuclei. And you can also see that in instances, for example, you could even end up with quadrupole-like configuration. The other point that is important to make is, of course, is that you can, in principle, if you think you are really making a magnetized plasma, you have some control over the magnetic field by changing the impact parameter of the collision. And so here you can see an example. So in this particular case, you see the electric field. And the point here is that there is some remnant of the electric field. It's never quite zero. And of course, if you have an asymmetric system like, say, copper gold, of course, it can play a role. That's not the main subject here. The other point, though, to make sure it's clearly understood is that the magnetic fields that I'm talking about here are sort of the initial magnetic field in the collision. And of course, what one knows is that, you know, these are fast moving objects. And of course, they will lead to relaxation of that magnetic field. And the extent to which that, how fast that relaxation occurs is largely dependent on what we know about the conductivity of the plasma, which of course we don't know a lot. So that means there is some uncertainty. While we can predict reasonably well the magnitude of the magnetic field initially, you know, since there is time required to sort of equilibrate or come close to equilibration of your plasma, one doesn't know what the full extent of that magnetic field is and whether or not it is large enough to drive the signals that is of interest.
Roy,
Now,
sorry to interrupt you. Are you using a pointer or not? I don't think we can see that.
oh, you can't see the pointer?
I don't think so.
Let me see if I can pen pointer. Is that better?
I don't think.
No, we don't see your cursor.
I don't think we see it. We can proceed as is, but then keep that in. Oh, now we do see the laser pointer, I think.
Okay.
Yeah,
Can
yeah,
you see
yeah.
it? Okay. All right. I'm sorry. Okay.
I'm not sure. Can you move it around so we double check?
So you see it now?
I don't think it's moving though.
Well, it's not moving somehow. Well, let's forget about it. Yeah.
So I think just keep that in mind that we probably don't see the pointer. So saying if you need to bring attention to a specific point somewhere.
Okay, then I will use language to be a little bit,
Right.
yeah, because I was assuming that, yeah, okay. So let me go on. So here's the key point, which of course is crucial here, and that is that in the magnetized plasma that one makes, the thinking, of course, is that if you had topological changing transitions, that could lead to a chiral imbalance between, let's say, the right-handed and left-handed fermions. And this is often characterized by this axial chemical potential. And the essential point, of course, then is that this chiral imbalance in the presence of the strong magnetic field, then that is what would then become the driver of the anomalous transport. And so that's sort of the backdrop there. And there are two principal anomalous processes. Of course, everyone knows that there are many, but for the purposes of this conversation, I think it's better to narrow the scope. And the two that I really want to talk about because they handshake very well is the so-called chiral separation effect. And of course, in this particular case, what one has is that basically you drive an axial current. This is a chiral axial current when, of course, you have a strong magnetic field, and of course, the associated vector chemical potential is non-zero. And then the other, which is pretty much complementary, is the chiral magnetic effect. In this case, you have a vector potential, a vector current, which of course is associated with the axial chemical potential. And I mean, if one just think about fermions in a magnetic field, then you know that the lowest Landau level is chiral, and most of I guess people are familiar with the fact that this is this imbalance then is a normal phenomena that one would expect. Okay, so another very crucial issue is that by virtue of the mechanism of these currents, then one should keep in mind that they have really important consequences for QCD, because if one was able to confirm, for example, the chiral magnetic effect, then of course it means that one, it would imply that one is actually having access to the topological effects in QCD on the one hand, and the other is, of course, that one expects significant chiral magnetic effect only if your fermions are essentially massless. So that means then that would then give you some access to some interplay with how chiral symmetry might be restored, and so on and so forth. Now, of course, once one understands that such effects exist, and we know they do. So, for example, in condensed matter physics, this has been fairly well established. So the issue is whether or not one can find it in Avion collisions. And the question then is, how do you do that? And let me just back up here and just say that in the case of the chiral magnetic effect, what this does is that it effectively drives a dipole charge separation. Now, obviously, the magnetic field is not always pointing up. And of course, one doesn't have full control of what the imbalance is. So of course, one will flip back and forth. But the essential point is that that has an influence on the azimuthal distribution of the particles. And that dipole-like guy, let's say we can measure that fluctuation, and that is related again to this axial chemical potential times the magnetic field. Now, on the other side, you can have a very nice coupling between the chiral separation effect and the chiral magnetic effect. And effectively, then that leads to the so-called chiral magnetic wave. And of course, the net effect of that is, of course, to drive a quadrupole-like charge separation, as I've tried to indicate here. So it means then that depending on the particular values of chemical potentials, then one could either drive a case where you have a quadrupole where the positive charges are at the tips and the negatives are at the waist, or vice versa, and so on. And so the main thing then is the way one then tries to establish these anomalous transport features is then to try to detect and characterize both this dipole-like charge separation and the associated quadrupole-like charge separation. So that's what one actually tries to measure experimentally. So what does this entail? What this entails is that you construct a correlator which can measure charge separation, let's say a dipole-like charge separation, or the associated fluctuation or variance along the direction of the magnetic field, and also a quadrupole-like associated with the magnetic field. Now, this is, of course, not a new story, because people have been, evolution, for example, many years ago. Here, I don't know if this is the original reference, but it should be close, all the way back in 2004. So in principle, we're talking, 16 or so years ago. And the basic idea is that this is now affectionately termed the gamma or so-called delta gamma correlator. And effectively, the whole point is that the correlator is designed to try to measure the difference between the charge separation. And in this little diagram here, you see the magnetic field is pointing down, and you see this particular configuration is showing you the separation between positives and negative charges. What is the problem? The problem, of course, is that there is other phenomenology in the event. There are resonance decays, there are flow effects, a whole bunch of stuff, and we're going to collectively call that the background. And even from the original starting point of this correlator, the authors already knew that backgrounds do complicate the signal extraction. And so for many, many years then, the whole point then was how to bring this background under control. And there have been many very clever schemes used to some degree, but basically what I want to say here is that that story is not quite settled. And this is a recent STAR publication for Physics Review, Physics Letter B, which shows a comparison, for example, of this delta gamma measurement as a function of centrality. You could think here, this is charge particle multiplicity, but you can treat that as a proxy for centrality. And effectively, the message that I want to convey here is that one is comparing the heavy ions to that of the small asymmetric systems like P goal and D goal. And as I tried to show in that little figure above, the essential point here is that in small systems, the fluctuations are substantial. And therefore, what that means is that the magnetic field is not reliably aligned, or let's say perpendicular to the reaction plane is not, approximately perpendicular to the magnetic field. So basically, what that says is that if those fluctuations are large, then you do not expect a CME signal, or let's say charge separation associated with the chiral magnetic effect, because that would have to go along the magnetic field. But of course, there's no correlation between the magnetic field and the plane that you're measuring. So that means that technically that should be a null signal or background for those small systems. And effectively what you basically can see here is that the signals, at least in the region, which unfortunately this is covered up a little bit, but if you look right around where it says star, that's where you can convince yourselves that the blue open circles and the red ones are sort of overlapping. So that would then suggest that there is no distinction between the two systems. The same is sort of true over here, again, with slightly scale variables, but the essential message is the same at the LHC. That means you can take lead, P lead, and you can then make the same argument. That is, I compare the measurement of these small systems where I don't expect a signal to the larger ones where there is a possibility that there might be a signal, and lo and behold, you see that there's hardly any distinction. So the backdrop of this then is that at least the conclusions were that backgrounds of whatever kind are sizable, and they could account for most, if not all, of what the correlator is measuring. Those are not my conclusions. Those are the conclusions of the authors of those works. The question one can, of course, ask is, could one make a more discerning measurement with a different correlator? And what I hope to demonstrate is that one can construct such a correlator and hopefully, take a look to see how that correlator behaves and what the consequences are. Let me just also quickly point out that for the quadrupole measurements, the quadrupole charge separation, the traditional suggestion has been to measure the so-called charge dependence of the elliptic flow, and measure that as a function of the charge asymmetry. So that means then that you have an event, and effectively you would then build your delta V2. You look measure this elliptic flow for negatively charged particles versus, say, positively charged particles. And then, of course, you can do that as a function of slices in the asymmetry. And the argument, of course, then is that you get this sort of pattern, which is the second plot on the bottom. And that would then convey that slope R would then carry information about the magnitude of such a signal. Now, very quickly thereafter, there were other authors, for example, who could take a purely background scenario and argue that one could get a similar dependence. So it means then that, doesn't mean that there is no signal present, it just means that the correlator has some trouble to discern between signal and background, because background and signal behave quite similar as a function of this charge asymmetry. And experimentally, for example, at the LHC, one can measure this R and use the same argument again. You can measure it for P lead, where you don't expect any signal, versus, say, lead. Or let's say, even if there were a signal, you wouldn't expect it to be identical to that of the lead. So again, you could leverage the same argument. But an equally important issue is that if you do this relative to the psi3 plane, then, of course, the psi3 plane can't measure a chiral magnetic effect, because the psi3 plane is completely decorrelated from the psi2 plane, and consequently is uncorrelated with the direction of the magnetic field. And so that then says that if I measure this R for both the psi3 and psi2 planes, and they are essentially the same, then that speaks to the possibility that there is not much of a signal. And of course, you can ask the same question again. Can you then devise another correlator which might have better sensitivity, as well as the ability to make a distinction between these common and well-known backgrounds? So let me now speak to such a correlator, and let me give you the rudiments of what the idea of the correlator is. I will then just quickly show you operationally what one can do, but spend more of the time on showing you results from it when you test the correlator. So what do we actually do? So the thing, that object which is in that square bracket there, this object, what does it tell me? It says that I'm going to make this R correlator, and I can make the measurement relative to mth order event plane. So M means that it could be, for example, the regular psi2 plane, or 3 would mean psi3 plane. And if you wanted to extend this, you could go to, say, 4, but for now we'll focus on 2 and 3. And D is just meant here to mean that when D is equal to 1, then we're making the dipole measurement. And when D is equal to 2, we're making a quadrupole measurement. What is the story? The story here is that we're using the same correlator and just investigating different moments of the distributions from the correlator in order to pin down phenomena which in principle should be complementary. So that's not a bad thing. So we build this ratio. So let's just look what the ratio, what the numerator is doing. So the numerator is measuring charge separation along the magnetic field. Of course, that could be quadrupole or dipole. The denominator measures charge separation in the plane, or let's say perpendicular. You know, of course, none of this is precise, right? Because remember, there are fluctuations. So when I say along the magnetic field, I mean on average, roughly, there is going to be a distribution. And so you see then that the denominator of this ratio does not measure a chiral magnetic effect. It can only measure background. And the idea, of course, is if my numerator has signal and background, and my denominator has background, then that ratio has a strong possibility that I might be able to sort of cancel out some of the background effects. Now, why do we measure with respect to psi 2 and psi 3? Well, same story here. And the story is very straightforward. The psi 3 plane is not, and I repeat, is not correlated with the direction of the magnetic field, which is on average perpendicular to the psi 2 plane. And so what that then means is that we have a null correlator in psi 3 because it can only measure background. So it is sensitive to background, but largely insensitive to a CME or CMW driven signal. So that's a crucial point. Now, we also can do measurements similar to what I discussed previously, where one can compare small systems versus large systems for the reasons I described earlier. That is, in small systems, you don't expect a strong correlation between the psi 2 plane and the magnetic field orientation, like in the avions. And so what that means then, that technically what that translates to is that your psi 2 for correlator for small systems should sort of be comparable to the psi 3. Let me say that slightly differently. It means in small systems, when you measure with the psi 2 plane, because there is no correlation, it's roughly as if you're measuring with the psi 3 plane. And so that means then that you can use this as an excellent benchmark, because you can try to measure in systems where you don't expect a signal and check to see whether or not it comes out according to what you might expect. Here, I'm not going to say much, but just to say that operationally, it's relatively straightforward to measure these correlation functions, which goes into the R correlator, okay? It follows the standard techniques. You simply make a ratio of distributions. And the only important additional point that I want to make is that the reference is always shuffled events, meaning that in these ratios that you build, let's say here, the difference, of course, for each of these correlation functions which one makes, the difference between the numerator and the denominator is only in the charge shuffling. So that means everything about that event in the numerator and the denominator are identical except for the charge dependent effects. So shuffling of the charges within the event breaks the charge separation. So this branch over here is sort of just saying what one does with the numerator. And this branch over here just says how you construct the denominator. And the fact that you can do this for different moments, d equal 1 or d equal 2 means then that you can try to measure charge separation, which is sort of dipole-like or quadrupole-like, okay? And so now what I will say here, of course, is that one of the good advantages, at least from my perspective, with this particular scheme, again, is that we're using one common operational framework for both types of measurement. Now, One could take you through some of the details as to why this correlator should work, or a whole song and dance. There are lots of technical details which I don't think is useful for this particular presentation. But what one can do, since a picture is worth 1,000 words, is that you can use existing models and try to demonstrate how this correlator functions with existing models which have been modified to include signal, models which are not including signals, and models which incorporate both signal and background. And this is what we've tried to do, okay? Now, let me just say that this is non-trivial. And the reason it's non-trivial is because these are the same models which are used to compare to data or reproduce data, like the spectra, the particle yields, the V2, V3s, all the anisotropic flow, and so on and so forth. So to a good extent, what that means is that these models then should more or less capture the essential features of the background. And then, of course, if you're clever enough, which we have lots of friends who are clever, you can also introduce signals. So in the hydrodynamic model, so this is a so-called anomalous viscous fluid dynamics model, then one can introduce a signal in the model, okay? And of course, there are also clever people with the transport model, this, and what they can do is that there is no explicit fermionic current in these models to mimic, but what they can do is they can mimic the effective charge separation that one gets by playing around with the momentum of the quarks and anti-quarks to sort of mock up what it would do if there was a real anomalous current there, okay? And of course, what that then means is that effectively one can put in a dipole which is characterized by this A1 coefficient. And of course, you can do the same thing for the quadrupole, meaning that you can play around with the coordinates of the charges or your quarks in such a way that you mock up a quadrupole. And what is the essential point? The essential point then is that you can then take these events and then use your correlator to see how well you can retrieve the signal, okay? Now, let me also point out two very important things, because it is very often misconstrued that somehow one expects to get back the output signal from these models should be exactly the input signal. That's equivalent to saying that the A1 should be the same. That is actually not true. So for example, if you looked at this A1 on the hypersurface of the AVFD, then of course, input and output would be essentially the same. However, there is a hadronic afterburner, and there are resonance feed down and things of that nature. So that means that there is signal loss in each of these models, okay? So one does not expect the input and the output signals to be identical for those reasons. The second point is that because of the way the signal is introduced in the AMPT model versus this AVFD model, one does not expect the degree of losses to be similar. In fact, in many papers which have been published, the authors of these models show that the signal loss you expect in the AVFD is of the order of, say, about 30%. And in the case of the AMPT, it is way larger. And the reason it's way larger is because in the AMPT, you have this partonic rescattering which is going on, which then basically makes you lose a lot more of the input signal as compared to say, AVFD, where the signal, the currents drive your asymmetries, and those are mapped at freeze out. Okay, all right. So that are two crucial things. Let me just quickly show that operationally this is straightforward to do. And the main point that I want to say here is that one, just build these distributions. You take ratios of these distributions, and then you take ratios of ratios. And of course, the point is that the convexity or concavity of these distributions, which are sort of Gaussian-like, will depend on the relative widths. And so the essential information contained in this particular correlator is in the widths of the distributions, okay? Now, one quick thing, just because when I start to show plots later on, it's important that you recognize the difference between this so-called delta S prime, delta S double prime. And that is just because one this particular correlator is subject to both trivial number fluctuations as well as the effects of the event plane resolution. And what this particular plot is designed to do is to show, for example, that you can take either simulated data or actual experimental data. And since you can adjust the number of particles in an event, you know, you can throw away some fraction of those particles. And in so doing, you can then change the number fluctuations, or you can change the event plane resolution, or you can change both. And so this particular exercise here is to show where you have your red squares, shows you where you take this set of events, and this is for 100%. And now the thing is that if you throw away 20% or 40% of the particles, you can see that the distributions are getting broader, as they should. And then going from left to right, the middle plot, you see that once you correct for the trivial number fluctuation, which it takes you from delta S to delta S prime, then you see that you're getting closer back to the 100% that you had before, which is the red. And then if you then correct for event plane resolution, you see that you can retrieve what you put back in. So what is the point? The point here then is that this says that at least from a model, let's say a data-driven perspective, we're able to influence both the number fluctuation as well as the event plane resolution, and are able, with our prescription, to retrieve that. So the corrections for the effects of both number fluctuations and event plane resolution is absolutely under control. So now, and it's, you know, of course, determined empirically and by data and simulations. Now, here, let me now start to discuss the sensitivity. So what does one do? What one does now is that you can now take, say, for example, the AMPT model. And as I tried to show in this particular figure, you can generate our correlator for events with no input signal, A1 equals 0, A1 equal 2%, A1 equal 2.5, 3, and so on and so forth. And basically what this then shows you is how the correlator responds. And incidentally, on the left-hand side, just as a basic sanity check, one can also show, for example, that the V2 are compatible with data from the same model, And if you make your V2 measurements relative to the reaction plane or the participant plane and so on and so forth, that you see the necessary effects of fluctuations and so on, which is what is encoded in the left plot. And the final takeaway, of course, is that you can look in figure F. What you can clearly see is that there is a linear relationship with the inverse width. This is exactly what you expect. But it has very important additional information, because what it says is that the extraction does not depend on which event plane we use. So that's important. The correction factors for number fluctuations and event plane resolution have to be under control, because it means that you can't reproduce the signal otherwise. And the inverse widths, of course, you know, if you follow this here, you can see that there is not a massive intercept. So that means then that you don't have a massive background. So the takeaway message is that at least in this model framework where one is simulating signal and background. And let me say that this background includes resonance decays, the typical fluctuations, local charge conservation, momentum conservation, the whole 9 yards, okay? So this is what's there. This says that you put in a signal, you can extract back something. You can do this, of course, with both models. And here, rather than showing you a whole set, what I can show you again is, this is the plot I showed you earlier. This is for slightly different centrality, but it isn't all that crucial. And here is the result for AMPT. Here's the result for AVD. You see that you have a linear dependence. Now, obviously, the amount of background which is present in the AVFD and the AMPT are not identical, and it's reflected in these intercepts. And by I, if you remember what I said was that the output and input are not going to be the same for both models. And by I, if you just roughly think that your intercepts are close enough to 0, you can clearly see that to get the same signal inverse width here, you see you need about 1% signal in AVFD, but you would need about 4% signal in AMPT, so there is about a factor of 4. But that is not a mystery. This is purely associated with the fact that the losses in AVFD are quite different from the losses in AMPT. What is most important is that you can clearly see that you have dependence. Now, let me now also show you that you can also do the same thing for the delta gamma, okay? The old correlator. And there are two takeaways here. So here you see for AVFD over here. So these slopes, of course, are going to be substantially larger than the slopes over here for the reasons I just described. And what is important here, of course, is that in the delta gamma, you expect a linear dependence on A1 squared, not A1. And that's clearly what you see coming out of the models, okay? What is most important here is to realize, okay, that your intercepts now are actually not very small. They're actually substantial. So if I come over on this plot, on this side here, this would be about 3% signal over here. You see that I'm going linearly as A1 squared, but you see that the intercept is a substantial part of this, okay? Now, what does that mean? It means that depending on the nature of your background, if you were measuring a fraction of signal, even when you have a decent input signal, you would be saying that the actual fraction is small, because fraction is signal over signal plus background, okay? And by the way, the same thing applies here for delta gamma as before. Okay, very quickly, let me just say that one can also do this for quadrupole. And of course, when there is no input, quadrupole, different percentages, you can see that the corresponding slopes are as I indicated here. And lo and behold, if you now plot those slopes as a function of input signal, you see that you have essentially a linear dependence. Okay? And so that means then that the correlator, at least in this model framework with the known backgrounds on the whole 9 yards, is able to detect what you put in spite of all of the other backgrounds which might be present. And just to make sure that it's understood that this is not hocus pocus, you see, one can also, in fact, sometime back, Dima convinced me that this was a plot that is absolutely necessary, and so it's included here in the simulations. And the point is that you can change the charge asymmetry, and basically now you can then plot the corresponding slopes, and you see that you have sensitivity as is inputted in the model. And so that then tells you what you need to know. So let me now quickly just come to one point, and then I show you the experimental results and see why you should believe that we're on a good path. So here's the summary for the inverse widths. Here is the summary. And I'm basically showing you again to point out that one has relatively good sensitivity and one does not have a tremendous amount of background, because the background would be reflected in these intercepts, okay? Now, you can do with the same events, you can now say, well, let me now take the same events from, say, AMPT. And identical to the same events, I can now go do, for example, my delta gamma versus A1 squared. And what you can clearly see now is that if I do this, you see that it's not that the correlator is completely insensitive to signal, it's that the background is a substantial part. So if A1 is very, very large, you have no trouble. However, if A1 is relatively small, you see that I'm going from here to here. And to highlight this point, let me just do one thing. What I'm saying is, let's imagine that in the AMPT, I measure a signal of about 3%. Okay? So a signal of about 3%, since it goes like A1 squared, this would be, 0.9 times 10 to the minus 3. So it would be here. But look at the difference between your intercept here and here. So that means if I wanted to, I could calculate a fraction of signal. In other words, of this total delta gamma that I measure here, what fraction of it is actual signal? And the answer is it's about 15%. Because you're dominated by this intercept, and this is a slow function here. So what is the takeaway message? The takeaway message is that one needs to be extremely careful when you measure fractions. In other words, when you do an exercise where you say, I'm measuring the fraction of signal which can be attributed to the chiral magnetic effect, that fraction is really a signal to background measure. It's not really a good estimator for the magnitude of the CME, because you could still have a credible A1, as I've demonstrated here, of say 3% in this particular model, but it translates into a very silly fraction because you didn't calibrate right. Okay, so that's the takeaway. So now I've oriented you. Let me now take the last several minutes and walk you through the experimental results very quickly to give you a feel for why I claim that the results seem to point in a direction which is suggestive of a chiral, or let's say an anomalous transport associated with the chiral magnetic effect. So let me show very quickly some of the R correlator. This is now R psi 2 and R psi 3. And lo and behold, you see that there is a clear difference between the correlator for 2 and the correlator for 3. Let me remind you, 3 can only measure background. It can't measure a signal. And so if this is representative of my background, then clearly, you know, one can sort of edge your bets whichever way you like. Let me just point out one thing here. This has nothing to do with whether or not the signal is convex or concave. It has to be concave for it to be a signal. But the background could also be concave. But the point is, let's take, for example, a hydro model where there is horrendous local charge conservation, which is effectively a charge separation. You see here, what one ends up with is that you get a concave distribution, but psi 2 and psi 3 are effectively quite similar. The data says the other way. If you go to the AMPT, where the local charge conservation is somewhat different, it's less extreme, what you can see is that this is sort of convex-like, this is concave-like. And so if you take this as a figure of merit, you would then say that these results are not incompatible, okay? Now let me go to the next case, where we compare large systems versus small systems. And now, again, this is what I showed you before for goal. And you will recall what I said about small systems. In small systems, of course, your psi 2 should be looking more like your psi 3, because the psi 2 results for small systems do not reflect a chiral magnetic effect or the charge separation associated with that. And so that's, again, I'm just flashing this to remind that this, of course, for the psi 2 is more in line with this. Now, let me just also say that it doesn't even have to convex down. Even if it was completely flat, that would already be sufficient, as is the case for P goal, okay? All right. Now, another thing that you can do very quickly is that you can also do Q2 selection on the data. And with the Q2 selection, we know, for example, that V2 increases, as I've indicated. These are experimental results. And what that then says is that when you change the event shape, you influence the eccentricity, you drive up V2. But if the thing you're measuring, the charge separation you're measuring, is not dependent on this, then you don't expect any influence. And lo and behold, this is exactly what you see here, is that the width isn't changing at all. Now, does one see that in the actual experiment? I mean, in the actual simulations? And the answer is yes. If you go back to the same AMPT, where you put in sort of roughly, you know what the widths are, so you can do a rough signal input, ballpark-ish, and you do a similar kind of analysis, lo and behold, you see that you would be insensitive, so it walks in that particular direction, okay? And finally, let me come over here on this other piece of feature, and that is that now what you can clearly see is that if I now change my centrality, when I change my centrality, keep in mind that my magnetic field will increase, and you can see that the widths, of course, the inverse widths, are sort of growing according to how the magnetic field might be expected to grow. Let me just point out that it is true that the V2 will also have a similar pattern as a function of centrality. But this is why we did this in the first place, to show you that this width here is not sensitive. In other words, the left plot is showing you that if you do your different Q2 selection, which is effectively tantamount to changing the V2, then you see that you have no sensitivity. So one could then argue that most of this guy here is associated with what we think could be compatible with a signal. And the dependence, of course, would go in the right direction. It would increase within the magnetic field, and also would reflect some of the issues related to the resolution of the event plane, even though we correct for that. And then, you know, depending on which model you're thinking about, you know, when I speak to my friends in AVFD, what they tell me is that they think, for example, that the axial charge per entropy is also influenced, okay? All right, and one little quick thing here is that, and this will take just a few seconds, because what I'm trying to say is that if you think that these things are signals, and the experimental measurements, then it's fairly straightforward to just go back to the models. And since we already calibrated these guys, it's fairly straightforward to infer what the corresponding A1 values would be. And if you take the AVFD A1s as the figure of merit, then you see in central collisions, it's about 0.25%, and then it rises in peripheral collisions up to maybe 1. And of course, there is roughly a factor of 4 difference between the A1s in AVFD and AMPT. One sees that in the simulation. So in other words, these would be basically saying the same thing. It's just because they measure different output values, okay? But it doesn't mean the signal is different. And as I indicated previously, if you now try to translate, you know, so let's say you take this guy here and you try to translate it into the equivalent fraction of signal from delta gamma, what you would end up with is something which is small. But it doesn't mean, for example, that there would be an inconsistency between the two measurements. It just says that one measurement is more sensitive and is calibrated. The other one measures some fraction, but in order to actually translate that fraction into a meaningful CME signal, one would have to calibrate that fraction, as I've tried to demonstrate before. And I'm just going to skip here and just make one little point that there is an isobar run. We think, based on AVFD measurements, that we can make a distinction between the isobars, but keep in mind that it is not necessarily true that because I can measure the signal for each isobar that I necessarily can measure the signal difference, okay? That will depend on the sensitivity. And the takeaway message here is that if we believe the magnitudes of the signals, let's say in AVFD, then it means that we would be able to measure, as indicated in the ratio here, that we would be able to pick that up. So what are we going to try to do? In the case of isobar, in the isobar measurements, what one can do is to measure for each isobar, as well as measure the difference between the two isobars, as well as measure the background difference, because remember, when we measure perpendicular to the reaction plane, we can explicitly measure the background for each isobar. So we have three things that we can nicely compare. And of course, we eagerly await. So I come to the end. I suspect that I've run over time a little bit. But my point that I wanted to make here is sort of twofold. One is that I think that when one constructs a correlator, it is quite useful. You know, even if one suffers from some model dependence, it is quite useful to check with model, with signal and background to see whether or not the correlator is performing up to snuff. And especially if those you know, models are including all of the very well known backgrounds that one has come to know and understand. And the final point that I want to make is that the measurements currently, as I tried to do in the last sort of 15 minutes or so, seem to point in a direction which says that it would be incredibly difficult to reconcile the Psi2 and Psi3 measurements, as well as the centrality measurements and the Q2 measurements with a purely background scenario. And I will stop here and take your questions.
Thank you very much. Thank you for a nice presentation. We have some time for questions now. So people in the audience, if you do have questions, please let me know one way or the other, either by raising the hand in the participants window or writing something in the chat window. I don't see any questions. Yes, so actually, let me use the opportunity and ask the question that I had. And my question is actually about the definition of inverse sigma, which you called the width.
Yes.
But somehow I'm not quite sure I understand the width of what exactly did you mean?
Ah, all right. So I should have been a little bit more, let's see, can I go back? Okay. My response time is horrible all of a sudden. Let's see if I can go back here. So I just need one plot. So I think this plot sort of tries to show the point, right?
Mm-hmm.
So in principle, right, if there was no background, the first plot, plot A, would be flat.
Okay.
And then you can see that the width, so what I'm saying is that, you know, these are sort of inverted Gaussians, yes?
Well, they look like parabolas to me, really, but fine.
Right? So if you know, so let me see if I can show you here that they are actually, you can approximate them as Gaussians. So the point is, you know, when you build the correlators, the correlations, oh, what is it doing? Oh my God.
I think you clicked too many times and it went.
Yeah, that's because the response has been a little bit slower than I expected. Yeah, I don't know why. Maybe my internet is not up to snuff. Oh. Let's see if it does move. Okay, so what I'm saying here is the correlation functions that one makes. What you're doing is, so here, for example, is one distribution. And here is the shuffle distribution. You take a ratio of this guy. And for the in-plane one, you would take a ratio of this guy. And you see, these fits between over these distributions are Gaussians, yes?
Mm-hmm.
And so, you know, if you take a ratio of Gaussians, you will get roughly a Gaussian, yeah? As long as you're sort of having the same mean.
Mm-hmm.
Okay, so that's the motivation for treating them as Gaussians. It turns out that we've tried other functional forms for fits, and it turns out that the answer, as long as you use a functional form that is capturing the change in the broadness of the distribution, then the answer is essentially the same.
Okay, if you could
So
keep
you can
this
see that
page.
the distribution is getting more and more narrow as
Well,
the
exactly, that's
signal
the
gets
point.
larger.
That's the
Yeah,
point.
so
The
that's why it's
narrow.
the inverse, right?
So
The bigger the signal, the narrower the distribution.
why don't you use the curvature of this roughly like a parabola? Isn't that the same thing?
I mean, so what I'm plotting here is assuming that this is, you know, I think it would be amount to the same thing, yes.
I see, I see.
Yeah.
Because somehow that would be much easier to visualize, at least when you're looking at this first 5 graphs, and then on the right, if you think of it as the curvature increasing, then basically that
yes.
would be kind of very natural to see right away.
That's right. That's right. Yeah. Maybe. But the thing though is that we need, remember, we need to link something back to A1.
Mm-hmm.
So, but my guess is that it would be the same.
Okay.
But it's easy to try. Yeah.
Okay. Okay, I don't want to steal all the show. Any questions from the audience? Because I could go for hours asking questions. Okay, I don't, oh, wait a second, there is, no, I don't think there is a question. It was something else, a comment about technical things. So I don't see any questions. So anyway, then if, in case people are still thinking about it, I have another question related to the this correlator that you are using.
Yeah.
In all honesty, I cannot see 100% clearly that this is necessarily point to the effects related to the magnetic field. It is the effects related to the orientation of the reaction plane, perhaps, but there is no clear argument that this will be also necessarily pointing anything related to the magnetic field other than the hypothesis that that effect exists.
Oh, no. So I think I made a tactical error by not walking you through the correlator itself. I decided that I was going to not, discuss in the actual correlator. So let's see here. So the correlator, this is the R, is a correlation ratio of 2 correlation functions, yes? And now what you have to do is build the numerator and then build the denominator for each correlation function.
Right,
so
but
now,
these correlators are telling you the charge distribution with respect to, well, assumed reaction plane.
Yes. So
they don't tell you anything about magnetic field.
Wait. Yes, it's true. So this is where I come to. So let's just make sure we agree first that the n delta s is really just measuring the projection along an axis which is roughly perpendicular to the reaction plane. So What I'm saying is that if you look, there is a sign of delta phi, where of course the delta phi is relative to the reaction plane. So what we're doing is that we're counting the average number of the projections of positive charges, perpendicular to the event plane, which is roughly on average relative to along the B. Now, obviously, we're going to correct for, event plane resolution effects, and we're also going to correct for trivial number fluctuations. So for the moment, then keep in mind then that yes, these projections that we're measuring for the separation are not perfectly aligned with the magnetic field, but we think that when we correct for the fluctuations and correct for the event plane resolution, that will be taken into account. So effectively, what we're doing is that we're really measuring an actual charge separation with these delta S's along, roughly speaking, the direction of the magnetic field, assuming that you take account of fluctuation in event plane resolution.
Okay. I would say it's still very, very indirect, because the assumption that you are making tacitly is that the magnetic field is roughly perpendicular to the reaction plane. For example, if you had only no chiral magnetic effect at all, but if you had only the flow V2, strong flow V2 that is driving an effective separation of charge because of the charge conservation, essentially you would see still the same.
No. Because remember, if it was only V2, then remember, if V2 does not have any charge sensitivity, then it cannot show up in this exercise. The ratio would just be 1.
No, but
now,
V2 will have sensitivity to charge.
If you have, let's say, a resonance decay, then of course you can pick up some of that. But that's supposed to be reflected in the simulations directly, right? Because the simulations include all of those, V2 dependent, V2 independent backgrounds. If you take the hydro, it would have, including the, say, flow effects, it would also include local charge conservation as implemented, as well as the local charge conservation that might come about from resonance decays and so on.
Okay.
So in principle, all of that is included.
Okay, thanks. I don't see any questions from the audience still. So I guess we will be wrapping this up.
Okay.
Last chance for everybody who are still here. If you do have questions, please ask. Otherwise, we will be ending. Using the opportunity, I would like to thank Roy for a lot of time preparing a very nice presentation and trying to lead us through intricate arguments here. And I think I got this way much better than before. So thanks. Thank you for your time. Thank you for presenting and making a very nice arguments about this topic.
All right.
Okay.